Hi everyone, my name is Gregory Kurtzer. I'm the technical lead and architect of the group that is responsible for implementing and building Savio, which is the compute resource, which we are going to be talking about today. So let's go back to the beginning. As Patrick mentioned, this all started via an email thread with Elliot and several other faculty members that stated that they wanted a computing resource, specifically, and I point out in this, a condominium computing model. So what is a condominium computing model? Well, in general, it is when faculty or researchers can purchase some component of hardware and add that into a existing resource and make that bigger, and then get some percentage of that resource back to them for their own use. So I want to take a moment and compare and contrast that to a model which some of you may be familiar with, and it's something that I've seen time and time again here on campus, up on the Hill, and at other institutions, where is a researcher needs a particular resource, a particular computing solution. So they get their funding. With that funding, they go and start investigating various specifications for hardware that they feel as though is going to meet their needs for their applications and for their research. So after doing that, then they go and talk with various vendors. And from these vendors, they figure out and try to decide, well, who's going to make the best, where's the best deal? From that, they now go to purchasing. They get the hardware, and then it lands on their doorstep in their office or in their computer lab. At which point, now they need to go talk with their grad students or their postdocs. This has never happened, right? Well, their grad students and postdocs, even though this is not really what they came to Berkeley to study, high-performance computing implementation and system administration, end up taking on this role, and they build this resource. And to further save money, a lot of times they'll put this resource into a closet. So this becomes a closet cluster. Well, in some ways, the Condo model, it replicates the good aspects of this and doesn't, it's not exploiting some of the issues with it. So let me give an example. From the financial perspective for a researcher, they have a capital equipment purchase that comes in initially with that hardware. From that hardware, then, they're handing it over to the postdoc or the grad student and putting it in their closet. Is there any cost associated with that? Well, sort of. It's a hidden cost. It's not blatant. So as a result of that, it is free to them. But it's not zero, because that postdoc or that grad student is now doing something and taking them away from what they're primarily there to do. So going back now and looking at the Condo offering, well, there's still that capital equipment purchase that they still need to make. That capital equipment purchase then lands not necessarily on the doorstep, and instead of handing it over to their postdocs and grad students, they're handing it over to us. We take that equipment, that hardware, and we incorporate that into a bigger resource that has additional file systems, additional system administration time, user services time, and as well as other benefits in which I'll talk about shortly. So there is a trade-off. And the trade-off is when you have your local system and you built it yourself and it's sitting in your closet, you do have full control over that. But that also implies now that you have a lot more time associated with it. You're losing the time out of your postdocs, your grad students, your researchers, and you're now spending the time system administrating your cluster. Now, looking at that on the other perspective with the Condo, you're not spending the time of the postdocs and the grad students. So it's not only free, it's zero cost, because all of the overhead in which you would be spending normally on maintaining and administrating this box is now being used on what was originally, what it should be used on, which is the research and necessary for, well, whatever those grad students and postdocs should have been doing to begin with. So there's another trade-off, which is when you have the cluster that sits in your closet and it's not being used, it's idle hardware. It's idle resources. Most people don't power down those resources when they're idle. So as a result, it's still consuming electricity, it's still running, but it's doing pretty much nothing. Now, in this model, with the Condo model, idle resources can now be reutilized for other purposes. So it's never really wasted. Because of that, there's another aspect, which is someone else might be running on your hardware when you need it. And as a result of that, there's going to be a small but reasonable, or possibly a small but reasonable amount of time you would wait when you submit a job. Does that make sense so far? Yes. Seeing lots of nodding heads, yes. So the point is that there is a trade-off. And with the Condo model, the trade-off, I feel as though, is you're getting a much more return on your investment than if you were to manage it yourselves. But from the financial perspective, it's really the same. It's actually even better because you don't have the zero. You have a zero cost when you're dealing with Condo. Anyway. With that, whenever you have a Condo compute solution, you do have a relatively high barrier to entry in the form of the hardware resources that you need to contribute to that pool. So we've now introduced the faculty computing allowance. And as Patrick mentioned, this provides free cycles to individuals and faculty on campus. Now, it does that in 200,000 service unit chunks, which are basically core hours. And these are refreshed annually. If you come in mid-year, that is prorated, so imagine it would be 100K. As I mentioned with compute, you get much more, with the Condo offering, you get much more than just compute. You also get the file systems, you get training, you get user services and various other bits of support. More features I'll go into in just a moment. But the point is that you're getting more than just the compute cycles. You're actually getting a whole service portfolio associated with that. To get the allocation, you request it via a survey. I believe some of you have already gotten this in your in an email that was sent out. And if not, we can make sure you have access to that. Right now we are in early user stages, and that access is primarily based on the readiness, your readiness to run on a system like this. We want to start off with the low-hanging fruit, the applications and the users that have already run on systems like this and that are ready to run on systems like this. That way we can focus on if there's any bugs or tunables that need to be fixed within our implementation. We can focus on that before we release it to the general public, which should be available by fall semester. Okay, now let's talk a little bit about the system specification. So earlier I made the analogy to a closet cluster, and that is a resource that a lot of people are familiar with because this is what we've been doing for the previous 10 to 15 years whenever we need a compute resource. So using that model of what the experience should be like from the user perspective, we architected this system to emulate that as much as possible to create a really smooth transition going from the closet cluster onto a bigger facility and a bigger resource like this. So, for example, typically within a closet cluster, you'll end up with a master node, a single master node that has many roles. Some of these roles are file systems, interactive logins, scheduling master, file systems. I think I said file systems. Well, they're really important. Speaking of, within Savio, how we handled the file systems was we broke the file systems into two components. And we did that to really emphasize what is the best aspect of each one of these types of file systems. So the first one is home directory storage. Home directory storage really is where you need to rely on that data. You know that whatever you put in your home directory is something that you intend to keep. So we've purchased into an enterprise storage solution for the home directory storage. Now, whenever you're talking storage, you have trade-offs. One of the trade-offs would be speed. Another trade-off might be resiliency. Another one might be size. So with the home directory storage, we don't have necessarily a smokingly fast file system. We don't have a massive amount of space, but we do have resiliency. It is a strong enterprise-level file system, and it's being backed up. So count those two factors in, and what you're going to see is quotas, small quotas on a per-user basis. Reasonable-sized quotas, but they are on the small side. To balance that, we have a parallel file system, which Patrick mentioned we are implementing an upgrade to right now, which will bring it to just about a petabyte. And the idea of this file system is it's Scratch. It's very fast. It's very big. But if you really want to make sure your data is always going to be available, you got to put it in your home directory or find another place to keep it. And that is because a parallel file system, as advanced as it is, it may not be the most resilient place to put your data. Sometimes these things have failures. There's lots of possible points of failure in a parallel file system. So we know that, and we manage that appropriately by calling it Scratch. Other things that we do within that file system is we purge, or we reserve the right to purge. And that is because we don't have quotas. And to better enable the amount of space in the file system itself, we don't want to impose any sort of limits on how you use that file system or how much of that file system you can use. So we basically open it up to you guys, and then as it approaches capacity, we'll usually go through and ask the big users to truncate some of their stuff and to delete things that they're not using. But if that fails and we still need to become more aggressive, we'll do things like pruning the file system and going through and looking for things that haven't been accessed and used in a little while, and we'll automatically delete those. Okay, so those are the file systems. Now, with the previous model that I was discussing, the closet cluster, you have the master node, which serves many roles. Now, one of those roles is for logins, interactive logins. So typically people will SSH into the management node in order to compile their jobs, edit code, set up their runs, and schedule their jobs. Well, in this case, we actually abstracted out the login nodes into a small cluster itself. So as those nodes get more busy, we can either grow the amount of login and interactive nodes that we have or shrink them respectively. We've also introduced a data transfer node. The DTN is a specially designed system for ingress and egress of transfers of data. So we have this huge file system, but what good is it if you're on a very slow network connection? So the idea of the DTN is you're bringing in data or bringing out data as fast as we possibly can. It's on a special portion of the campus network called the Science DMZ, and it is tuned and it is as fast as it possibly can be given the considerations of the hardware and the underlying network. So additionally to that, we have compute nodes, which are grouped and delineated based on roles. So I wanted to also include a picture that describes this. Okay. So coming in, here's network. Coming in, here's the BRC firewall. This is a firewall appliance, which as you're SSHing in or trying to get access, it will basically redirect that access into the login nodes. The login nodes are a cluster within its own right. You'll get an interactive SSH bash session on the login nodes. The storage you'll see right over here. This is the home directory storage. And to the right of that, you're going to see various management servers. There's actually more than one. We have several of them for provisioning, for monitoring, etc., scheduling. Now, this is the primary Ethernet fabric. Underneath this, we have, you'll see our Lustre file system. This is the fast Scratch file system. Our groups of compute nodes, and our data transfer node. Notice the data transfer node is circumventing the firewall, and that's because this firewall can't speak at the rates in which this data transfer need would basically require. This is running a firewall, but it's a local firewall as opposed to going through a firewall appliance. One last thing to note is that there is another network connection here, which is the low latency, high speed InfiniBand fabric, which connects the file system, all the compute nodes, and the data transfer node. A little bit more details about the specification of the hardware. We have two primary groups of compute nodes at the moment. We have the general compute population of nodes, and we have our big mem nodes. They're pretty much the same. They all have 20 cores connected to the InfiniBand fabric, but as the name suggests, the big mem nodes has half a terabyte of memory, where the standard compute pool has just 64. As far as the software stack goes, we're looking at Scientific Linux, which is a binary and ABI compatible version of Red Hat Enterprise Linux 6. We offer various parallelization libraries, OpenMPI, OpenMP, of course, POSIX threads, Intel compilers. We have several different versions of the Intel compilers installed. This is a licensed product, and we've already paid for that license for you. Job scheduling, we are running Slurm. Another important thing here to mention is software environment modules. And it's very important because this is what allows people the freedom needed to run different versions of compilers, different versions of their applications, and different application suites, all on the same system without competing or conflicting with each other. So software environment modules allows one user, for example, to be using the Intel compilers with OpenMPI and their application stack, and someone else right next to them running GCC with a completely different version of OpenMPI, etc. It also allows you to test drive different compilers and different application versions to see which one may perform better or not for your particular needs. So usually I don't talk about security in a forum like this, but I think it's important. And I think it's important because one thing that we've seen over and over again as I talk to scientists and users and whatnot about security is that there is a fairly violent knee-jerk reaction within, and it's not just Berkeley campus, it's with a lot of users, to the idea of OTP or multi-factor authentication. Show of hands, how many people know what that is? Awesome, very good. There was just, Gary, who's sitting right back there, was just telling me earlier today that there is an article in the New York Times, I believe he said, from today, that was talking about, from the business section, that was talking about the best ways of mitigating hacking and having your accounts becoming hacked. And their number one solution, and I swear I wrote this yesterday before I heard about this, was OTP and multi-factor authentication. Now, this is because the biggest threat that we've seen over and over again is stolen credentials. Now, how are people getting these credentials stolen? It's not like you're writing your username and password and leaving it out in the open. It's not that at all. What's happening is people are trusting computers that they believe are safe because they don't have reason to think that there is an exploit, that they've already been exploited. So they trust these computers, and they type in their username and password into these computers, which have been exploited. And part of the exploitation is that they're running something called a keyboard or a TTY sniffer. And these TTY sniffers it's the equivalent of somebody sitting over your shoulder watching every single thing you type. And as soon as they see a login window open up, they take out their notepad and they watch everything you type. And then they send that over to their friends. That's basically what's happening. And UC campuses, or university campuses, much bigger than just UC, as well as commercial industry across the board, is plagued with exploited systems where people don't know that they're exploited. The only way around this is OTP. And we've been able to circumvent these sorts of exploits on our systems where it has taken down other centers and other facilities. So I can't stress enough how important this is. And I'm bringing this up now, as I mentioned, because there seems to be a knee-jerk reaction against this. So I'm trying to make as many people aware of this as possible because it's a very important aspect of security and keeping your data safe. And even if you're sure that your data is safe and your credentials are safe, you can't necessarily vouch for the people on the other side of campus. So we have to make this policy. We've done everything we can to make this easy to learn and easy to work with. And if you have any questions or need any help setting it up, we're happy to help. Okay, so moving on. Future services that we are implementing and in the process of implementing right now. First one is serial/HTC jobs. When we first built this resource, as Patrick mentioned, we knew that there was an HPC contingent on campus that required this, specifically an HPC solution. We knew, though, that there was also, this doesn't cover everybody, that there's other needs within campus. So we knew that, but we didn't know exactly what those needs were going to be. So what we did is we implemented the HPC component, and then as we grew that and as we talked to more and more people, we learned exactly what was needed from the HTC and the serial perspective and other aspects. And from that, we've learned that we need to invest in specialized hardware for doing serial and HTC type jobs. We are building that up with 12 core nodes, 128 gigabytes of memory, and PCI-based flash storage. The flash storage seemed to be very important because a lot of the nature of these jobs seem to be that they're doing lots of local I/O via temporary files. So of course that's not for everybody, but for the particular mix of what we were seeing, that was very important. Again, we're calling this serial/HTC. The specific role is really anything that is less than or equal to one node. So that could be, if it's a 12 core node, it could be somebody's using 6 of those cores, which leaves half of those cores still available for someone else to come along and run another job. So the nodes are shared between jobs. Now that's a very different architectural perspective than you would see in an HPC system where nodes are dedicated to a single job.
You might want to say what HTC is, Craig.
I'm sorry, say again?
Define HTC.
HTC, the acronym specifically stands for high throughput computing. Okay, another aspect that we are building up right now is GPU support. So the GPUs are traditionally optimized for massively parallel applications and algorithms. And we want to, as we spoke with various researchers, we saw that the best way of implementing this is to build a lightweight node, a node that is not a huge powerhouse but can properly host as many GPUs as we can fit into that box. So we ended up with settling down on 8 cores per node, 64 gigabytes of memory, and we're going to load those up with 2 NVIDIA K80s, which is a pretty substantial GPU resource. So that concludes my section of this talk. Are there any questions? Yes?
With the cluster and the security, when we're off campus, will we need a VPN? And will the one-time passwords work when we're traveling outside the U.S.?
No and yes, respectively.
Okay. Thanks.
Sure. Anything else?